Okay, so welcome everyone to this EFCE Spotlight Talk organized by the energy section of the EFCE. The topic is process integration for the energy transition in the industry. And before going into an introduction, I would like to pass the words to Giorgio, who is from the EFCE.
Okay, thank you, François. I'm Giorgio Veronesi. Good afternoon to everybody. I'm Giorgio Veronesi, Executive Vice President of the European Federation of Chemical Engineering. I've been EFCE. I've been in the board of EFCE for 5 years, and currently I'm in my second term in this position where I'm responsible for the operational, economic, and financial matters of the Federation. I'm a chemical engineer by training, graduated in Padova, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects abroad with several assignments overseas. I'm very happy to be involved in the introduction of this webinar on energy, as during my professional life, I had the opportunity to participate to many energy-related initiatives, from development to construction and operation, and I'm really interested in such an important subject. Let me say something about this webinar series. EFCE is organizing a series of free virtual spotlight talks on significant topics of chemical engineering. 11 of our technical groups, working parties and sections, like the energy section, are delivering short sessions of 3 or 4 talks by leading industrial and academic experts on chemical reaction engineering, education, energy, this is the second one on energy, loss prevention and safety promotion, mechanics of particulate solids, mixing, multi-phase fluid flow, process intensification, quality by design, static electricity in industry, thermodynamics, and transport properties. Each session will focus on a key subject, but the series as a whole enables attendees to sample topics in areas they find interesting, but not otherwise have had the opportunity to attend before. In this way, we want to encourage cross-fertilization between specialist areas. Let me say something about scientific collaboration. The EFCE promotes scientific collaboration and supports the works of chemical engineers and collaborating professionals in 30 European countries, representing more than 100,000 chemical engineers in Europe. EFCE working parties and section cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. And this is a practical example of what they are doing. Before concluding, I would like to thank all the people who work hard inside the working party and section and in EFCE for this initiative to happen and to be successful. In particular, I would like to thank Martin Pou in Toulouse and Ines Hondorf and Horst Massong in Frankfurt, who did most of the conceptual setting up and practical activities for the webinar. Having said that, I would like to thank you for your attention and wish all the speakers and attendees a fruitful and successful webinar, and I give back the floor to Professor François Marechal of the Ecole Polytechnique Fédérale de Lausanne in Switzerland, co-chair of the energy section of EFCE. Thank you.
Thank you very much, Giorgio. So it was really a pleasure to be to participate to this effort of creating this those spotlight talks. And together with Thore, we have decided to make a joint effort, and it is really because we would like to really promote the international collaboration. So we decided to have this seminar on process integration and the role that process integration will play for the energy transition. So Thore is the chair of the Industrial Energy-Related Technologies and Systems Initiatives from the International Energy Agency. And myself, I'm the co-chair of the energy section of EFCE. So I'm going to just introduce in few words what is the energy section and what is what are the missions of this energy section. And Thore will then afterwards introduce the role of IETS within the International Energy Agency. So the energy section is a new initiative. It has been created 2 years ago from the EFCE. It is headed by myself and Professor Fabrizio Berntsson from Padova. Sorry. The energy section is by essence a transdisciplinary, and this is the reason why we are speaking about a section, because it is mainly looking at different domains, and we realized that it was not possible to address the problem of energy in a simple way. Therefore, we have divided our contributions towards two main aspects. On the one hand, the energy for the chemical engineering and in chemical engineering, recognizing that the energy is the driving force for the industrial processes. The energy is also part of the wastewater and energy nexus and is involved in all the aspects that leads to an efficient conversion of the energy for the chemical processes. But on the other hand, we realized that the chemical engineering can be a key actor for the energy sector. Think about the fuels and the catalysts that are developed for in the transportation and power sectors. Think about biofuels and bioproducts. Think about integrating the renewable energy resources, especially solar, into the energy system. Think about capturing carbon dioxide, deciding what to do with this carbon dioxide, and all what is related to the energy storage for the energy sector. And so our goal was really to highlight what is the role of chemical engineering in those domains. So we have organized ourselves with subsections or subtopics that are each one held by a chair and working party representative. Sorry. And the idea was really to highlight the different aspects of energy in chemical engineering and chemical engineering in energy, and have an animation that allows us to serve as a relay towards the other sections or the other working parties of the EFCE. And our mission is to try to reinforce the collaboration and the cooperation between the professionals and the academia in the field of energy. To provide also a discourse that shows the importance of chemical engineering and the opportunities that are created by the energy transition. We can also offer support for having a knowledge for the members of the EFCE members when it comes to the role of the efficiency and the way to mitigate the carbon dioxide emissions and the integration of the renewable energy sources. And with this, we would like also to be sure that, or to highlight the cross-fertilization between the working parties with the special topic of energy, to finally give decision makers from the business or from the society with a reliable knowledge of how the chemical engineering can help in finding solutions, and of course also show how the role of education of chemical engineers and what they can play, the role that they can play for the energy transition. So those are the missions. And for doing this, then we are active in the organization of conferences like the ECHE conference, ESCAPE, CHISA, where energy and chemical engineering is always involved, highlighting the contributions of the chemical engineering in those topics. And we have also other dissemination activities like creating keynotes, seminars like the one of today. And we have also an initiative in creating open access research topics editions in which we would discuss the challenges of chemical engineering and energy. And of course, the last element is to really promote the international collaboration, and the meeting of today is the proof of this collaboration. And from there, I will pass the words to Thore, who is representative of the initiatives from the International Energy Agency. Just before Thore starts sharing his screen, I would like to highlight the fact that there is a Q&A button that you can use if you have questions. We will follow this Q&A to take the questions from the audience and then to give the answers during the different presentations we will have today. So Thore, the floor is yours now.
Have you stopped yours? Can you see my slides now?
Yes. Yes.
Very good. Thank
So,
you, and good afternoon, everybody. Yes, I am a chair of the IETS collaboration within IEA, Industrial Energy Related Technologies and Systems. I will take you through a little of what we are doing, and I will do it very quickly, just showing some slides, and you can look at them afterward for details, and also, of course, go to our webpage. We are an international collaboration, and we have, for the moment, 10 member countries: Austria, Canada, Denmark, France, Germany, Italy, Netherlands, Norway, Portugal, and Sweden, and a few others are knocking on our doors. And we have also a sponsor organization from Finland, Ireland, Japan, and Switzerland. We work mainly with collaboration and having activities, not one project, but sharing projects that we have ongoing in our groups and countries. So it's mainly networking. We have what we call annexes, that is working groups, and you see a number of them here, and I don't go through them, but you see that we are working in many different areas. Actually, our work deals with, in principle, all types of energy and process technologies and systems in industry, and all types of industry. So we are rather broad, but this is what we have concentrated on we are doing for the moment. We also work with lots of workshops and conferences. And you see a list here of a number of recent workshops. On our web page, you can find a number of different reports, and here you see some recent reports. The background for this is that we earlier worked together in process integration areas. For the moment, we have no explicit annex on process integration, but we have discussed many times to start that, to have more international collaboration in that area. And we had a workshop in Berlin in 2017 with experts about process integration, and the report from that is on our webpage. And more recently, we had a big workshop in Vienna last autumn, 1 year ago, which was on deep decarbonization in industry, with around 50 participants, invited, only invitees. and the report from that is also available. We had a number of aspects that you can see here on a number of aspects on how to have more deep decarbonization. One of those being session 3, industrial systems, and there it was discussed to a large extent about process integration. So here we see the 4 areas in which we discussed, and in all of those areas for systems, process integration is an important part. And we discussed that process integration methods have even more a higher interest now when we have to make big changes in industry in order to have GHG mitigation in different ways. And François mentioned about that also earlier. But also combining that with what we call ex-ante evaluation, and that is a method for strategic evaluation of radical changes given future conditions where process integration should be a part. Also, to create negative emission systems in industry, process integration should be important. And finally, industrial symbiosis, which is also very important for process integration. Those were the system aspects. I don't go through all the other aspects we discussed. And based on the discussions in Vienna, we identified 4 different areas, especially for process integration. And those areas are the ones we will try to deal with also today. So I mentioned them here. New methods for process integration in the context of energy transition to low emissions, high share of renewables and novel technologies. The second one is strategic planning of complex integrated industrial systems, taking industrial symbiosis, circular economy, future conditions into account, also with this ex-ante scenarios, as I mentioned. Third one is the importance of digitalization, and not the least also databases that we can have together for industrial energy systems. Examples, and I will mention a little later on about what we have done within IETS in that area. Finally, risk mitigation in the development and the operation of integrated industrial systems. So those are those things we will discuss, and which also will be highlighted in the presentations we are going to have. And I suggest, therefore, that we go on directly to the first speaker, and that will be Professor François Marechal. And his presentation will be on the role of process integration in industrial symbiosis for the energy transition. So please, François, I stop sharing my and hope that you can put on your presentation. Please, François.
Okay, I'm starting sharing my screen. Okay, could you confirm that you see my screen? Okay, so hi. In fact, what I'm going to do is to discuss about my opinion or my vision about process integration and how it can play a role for the energy transition, highlighting the different topics that Thore has just mentioned. So perhaps that's this is a summary of my talk to some extent, and I could perhaps even stop there. So what is there is an integrated system. So what you can see in this integrated system, I hope that you see my mouse, is that you have different industries. Those different industries are from different fields. So, and they can be integrated by exchanging heat, by exchanging mass flows, by exchanging waste, which introduces the circular economy. And this subsystem is at the end integrated into a bigger system, which is the energy system, which deals with the renewable energy supply, with the carbon capture and sequestration or reuse, and is also responsible for the energy management. So one could say, okay, this is already the summary, because at the end, the goal of the system integration is to understand all the exchanges that are highlighted here, that you can see in terms of mass flows, in terms of heat recovery, in terms of efficient energy conversion, being by heat pumping or by waste heat conversion into electricity. But also something which is perhaps important is that you can see that there is also this mention of a biorefinery, which deals with the use of biomass as a source for the future energy system. If we talk about the importance of the energy in the industry for in the energy sector, so industry in the world corresponds to around 32% of the energy that is consumed. And when we look at the industry, 74% of this 32% is in form of heat, and you can see that it is today mainly produced by fossil resources, and it can even be divided into different levels of temperatures, which is also very important because it defines the value of this heat. So 30% at the temperature below 150 degrees C, 22% in between 150 and 400 degrees C, and 48% above 400 degrees C. In addition to this, we know that we have different sectors, and those sectors have also different types of or share in the form of energy that is used. So you can have highly heat-intensive sectors like the food or the chemistry industry, where we can see that the majority of the needs are in form of heat. So the cement is also a good example, while there are other sectors which also need a lot of electricity. So this dual use of heat and electricity is very important. How do we approach this problem of efficiency? So the efficiency is really dealing with the fact that we would like to reduce the amount of electricity, the amount of heat that is needed in order to make raw materials product out of raw materials. In fact, something which is important here is first to realize that we are bounded by the mass and the energy balances, meaning also that if we are efficient in using the energy in the system, then the majority of the electricity, the energy that is consumed will go into product and perhaps flow of waste, and will not have to be released by in the environment. So how do we approach this efficiency problem? So typically we start by doing audits. Then we look at benchmarking to know if the technologies are good or not. And then we think about having a better operation of the systems. And then we try to say, okay, why don't we then try to recover the heat from the streams that needs to be cooled down, that creates a waste heat, to preheat the streams that needs to be heated. It's really what is related to the pinch analysis. And then we will ask ourselves, so what do we do with the waste heat? And the waste heat has two major possibilities. On the one hand, as it is released in the environment, it can be used as a source for heat pumping, or it can be used as a source for producing an extra amount of electricity by low temperature heat valorization. And then we have to ask ourselves, so what is the best way to close the energy balance? And we know that there are techniques that are well known, for example, the combined heat and power production. But we could also say that it's important to think about producing another form of power, of energy, sorry, not power, but fuel, together with the heat that we deliver to the system. Something that is important now is to realize what we can do when we want to realize to understand the energetics of the system. So the first is that we define the need for heating and the need for cooling. And then we realize that the deeper we go inside the process, the better we are in defining the profiles of the needs. So of course, I can always say that for a distillation column, I'm going to define the need as being a certain amount of steam at a given pressure, but it could also be better to look at what is the stream that needs to be heated. And this is going to change the profile and the opportunities for the heat recovery, meaning that, for example, I will be able to recover the heat, the waste heat from cooling requirements to supply the heat for another requirement. And each time I'm changing the profile, I have to realize that I will have to pay for this profile. The closer I am from the process, the process operation, the bigger is the area, the heat exchange area that I need, and therefore I will have to increase the amount of the investment that is associated. But by changing the interface, I will create opportunities for heat recovery, and I will also create opportunities for better conversion of energy, and especially for the by heat pumping. And of course, what you can see in this figure here is that we will reduce the operating cost, meaning that we'll need less energy because we recovered the energy. But on the other hand, we will have to pay for the investment that is related to the transfer of the energy or to the optimal conversion of the energy that we buy into useful energy for the system. What we can realize as soon as we start doing this analysis, it's that it will be very important to understand, for example, the conditions under which we will implement the heat pumps that I will remind you has not all a COP of 3. In fact, the integration of heat pumps into industrial processes allows me to illustrate the need for new methods. So heat pumping is the principle of taking heat at a low pressure and at a low temperature and making it available at a higher temperature. But at the same time, we have to choose the type of fluid, the working conditions of the fluid, the configuration of the system, and the compressor types. So it's a very difficult task. Looking here, for example, at the number of refrigerants that we have, and those are only the pure fluid. Associated to this, the different types of configurations, and those types of configurations can be represented into superstructures. Superstructures that are constituted of technologies. And here, for example, is the collection of technologies that we have just for the compressor. And of course, we have the same for the vessels, we have the same for the heat exchangers. Now, assembling the technologies into configurations, choosing the right fluids, can be done by using optimization techniques. And optimization techniques typically do not only look at the optimum, but more try to generate collections of solutions, like the one that are shown here. So you have a list of solutions with different types of fluids, with different types of configurations, each one being well integrated to the demand of the process. And once I'm doing this, then I will be able to optimize the efficiency of the system, but also the use of the system. So the case that I'm going to show you here is a case of a dairy process that is optimized, where we integrate the heat pumps, and the integration of the heat pumps shows that it is possible to reduce up to 50% the heat requirement for the system, and therefore also at the same time reducing the amount of heat that is released. Something which is important is to realize that I'm doing this for the dairy, but if the question is what is the potential of the heat pumps, then you need to have the representations of the different profiles of the different industrial sectors that needs to be modeled so that we can characterize what is the potential for heat pumping in the Swiss industry, for example. So what we have made here is that we have made a database of typical processes from different sectors, from you can see breweries, refineries, chemical processes, steel, which is based into a collection of subcomponents, because if you think a refinery, it's not only a single process, but it's a collection of integrated processes, each one being balanced or having different flows inside the system that allows to generate typical profiles that can be used to assess the potential for the heat pumps, which then can show what is the impact at the level of a country when you know how much of each of the the consumption of each of the sectors in a typical country. Something which is important here is that by building this database of typical processes, I was able to assess what was the potential of for the heat pumping, but I was also able to say, okay, but now why not merge or integrate different types of industries? Having the profiles allows me to make the different types of industries interact one with the other, which allows me to plot a map where I'm able to identify what are the exchanges that can be done. And this is what we name the symbiosis. The exchanges that can be heat exchange, that can be mass exchange, that can require the development of networks that needs to be invested, that would also probably need to optimize the profiles of each of the industry so that they match correctly with the other one, so that we can develop symbiosis business models that realize the system integration. And here what I want to show is that there are mass exchange, there are heat exchange, and there are even here the storage that is then offering a service to the energy system. And there are several options, of course. There is the best option, but there are also all the options that perhaps do not realize the 100% of the symbiosis, because we have to think the system as a retrofitting approach where we have to adapt processes. Which means that at the end, we will not have only one single solution, but a collection of solutions that we will have to compare based on different types of key performance indicator. And when I'm showing here, so you have the CO2 savings, you have the net present value, you have also the different types of investment. And something that was interesting in this study is that the investment can be done by different parties. So you can have a third investor that is going to decide to invest in the pipes while still offering a lower price for the heat delivered to the different partners. And something which is interesting there is that by using this kind of tools based on optimization and based on the systematic generation of solutions, we are able to see where are the most profitable region. We are able to test the sensitivities on those solutions to identify at the end who is going to, what is the benefit of the integration. Another dimension is what I mentioned is the use of biomass. So when you have biomass in form of woody biomass, typically, or waste biomass, you can convert it into stored energy like synthetic natural gas or synthetic fuels. The byproduct is carbon dioxide, and there is a subproduct that comes from the chemical reaction that is heat. And heat can be used to drive processes. And so one example is the process of producing ethanol. So it has a 32% efficiency, but you have waste there. The waste, it can be burned by combustion to produce the heat that is needed, and sometimes adding a steam cycle produce as well the mechanical power that is needed in the ethanol production. If now I want to do something better, what I can do is that I can produce from the waste biomass, so the unconverted biomass, synthetic natural gas. Synthetic natural gas, which will at the end double the amount of fuel that we produce from the same amount of wood. Still, and something which is interesting here is that I'm supplying the heat with the production of fuel. I can add the steam cycle in it, so in order to co-generate power, and then due to the energy balance, the amount that we extract in form of mechanical power cannot be converted anymore into fuel. But when we do the analysis of the system and we think about heat pumps, it means having a very good understanding of the full system integration. Then we can show that we can reach efficiencies that are very high, up to 73% in production of fuel out of biomass. And if you look from the beginning, so we have more or less a 50% increase in the efficiency of the system. The system integration here was just made in form of heat. So the heat is supplied from the synthetic natural gas to produce the ethanol. But sometimes we have to think of being much more integrated. An example is the production of pulp from biomass. Typically, the pulp is produced by recycling the black liquor, so the chemicals that are used to extract the pulp, and the heat is supplied by the bark boiler. But there is an alternative, and the alternative is to go to the gasification of both the black liquor and the bark residues into fuel and supply the heat and the chemicals back to the process so that we have a completely integrated version. Another dimension that needs to be also tackled is the integration of renewable energy. And I will discuss this in two different ways. The first one is on the integration of solar heat and or electricity into an industrial process, and what is going to be added to the classical approach of an industrial process is the need for the energy management that can be done by heat storage. The use of heat pumps is very important in this case because it allows to use the electricity that is produced by the PV panel, and it creates also competition between the solar heat and the electricity produced by the PV panels. So now we can see that we have a lot of technical options that could be the simple thermal panels or concentrated panels or electricity only PV panels or even hybrid systems. And we have to combine this with the heat pumps. And what we can see is that there is a possibility of making the system 100% based on renewable energy, but with something which is a very big constraint, is that sometimes it is 100% and sometimes, so for example, in January in Europe, you will have to still burn some fossil fuel. The advantage of this is that now we can show a list of mitigation options that can be proposed in the system by maximizing the heat recovery, by integrating heat pumping and then integrating solar energy in it. The solar that can be photovoltaic, that can be flat thermal, thermal, or that can be hybrid, or even using concentrated solar panels. Something which is showing here is that by doing all these actions one after the other, we can reach a system that is reducing its emissions by more than 80%. The last aspect that is here is the fact that the renewable energy is by definition stochastic. And so it introduces also the opportunity for the industry to play on the stochastic market of the electrical production. And this is done by optimizing the strategic operation of processes, taking into account the predictions of the electricity price or the electricity availability and the constraints of making products available at a given time for on the market. What we have shown here is that an approach that is applying the optimization allows to maximize the revenue, minimize the cost, or minimize the carbon dioxide emissions. And this is also very important because it allows us to then decide how to pilot the system and define what is the price to pay to minimize, for example, the emissions. Something which is also very important is the fact that the energy system in the future will have an excess of electricity, especially in the summer period. And this is not only the future systems like the one that is shown here for Switzerland, but it's also seen even today, where in summer there are some subsystems of the European grids that has an excess of electricity that needs to be used. So what can we do with this? The answer from the process integration is to look at the green boiler. So the green boiler that was producing heat and fuel already, we can also see that we are releasing carbon dioxide. Of course, what we can do is to sequestrate this carbon dioxide. So the byproducts can be sequestrated, still producing heat and fuel. But we can also then play with the electricity that is on the grid. So in the winter, we will produce in a normal way, releasing the carbon dioxide, but in the winter, what we can do is to take the carbon dioxide and convert it into more syn fuel by using electrolysis. and having an excess of electricity available. And I can even be more integrated by saying that in the winter, I'm going to send the carbon dioxide to the sequestration. And in the summer, I will use the carbon dioxide that has been stored to increase the amount of electricity that I can afford in the system and make more fuel out of it, and still producing the heat for the industry. And what we have seen by doing this approach is that instead of burning the wood into a boilers that would make a boiler 100% renewable, okay, we could perhaps use the combined heat and fuel production. And what we have shown is that in this case, a unit of carbon that is in the biomass can substitute up to 3 times more fossil carbon dioxide than a classical use of a boiler in the use of the biomass, in a classical boiler. And something which is also interesting here is that you can see that the break-even, which means the tax that makes the renewable energy system more attractive than the oil boiler, is decreasing with the amount of the break-even is decreasing with the quality of the integration, because at the end we receive a premium coming from the fact that we substitute the fuel that is produced, we still supply the heat, and we have a byproduct that is, for example, the carbon dioxide that can be sequestrated. So as a conclusion, we have a system that has made increased its efficiency, that has integrated different subsystems while using the waste as a raw material to make new products, for example, or to recycle, and producing at the same time the fuel that is needed by the energy system. We still have waste heat that is available. And of course, what we will do is that we will try to connect this waste heat with cities in such a way that we will be able then to use the waste heat, or to use the city as a way to evacuate the waste heat from the industry in an integrated system. A consequence of it is that the cities will need less energy resources. It means that when we do this integration, at the end, we will have to buy less resources to drive the city. And the example that is shown here is that, so we have made a fake city that was supplying all the products that it needs, and the services, so the heating and the lighting and the mobility of the city. And what we have shown is that if we integrate the industry in this approach, then we were able to make the city 100% autonomous, and we were saving 30% of the PV area that was needed to make the city autonomous. At the end, I will conclude by saying that the system integration needs to have a very holistic vision by looking at not only heat, but heat, electricity, water, and waste, thinking about optimal conversion of the energy, looking at the efficiency, thinking about cogeneration and heat pumping, looking at the integration of the energy resources by the use of the network. Always think about efficiency and the consequence of the inefficiency, which is the waste heat that needs to be recovered, but it makes this very site-specific or location-specific. We have to look at the industrial activities, the cities nearby, and the resources that are available, because we will have to look at the supply chains as well as the energy supply. We will have to create the interconnections, and for this it's very important to have this approach of blueprints to know where are the opportunities, and to build and plan the future energy systems with multi-energy networks. With respect to the methods will need to have a very systemic approach, looking at the efficiency and looking at the exchanges that can be done with the resources and the environment, and computer-aided methods that integrate the energy management, that look at not only the technology to invest, but the way that they will be operated, based on databases of available technologies, which have to be included into models. and that allows to use optimization techniques and superstructures to extract solutions in order to be able to generate multiple solutions that allows a multi-criteria analysis. So those are the needs for methods, which will allow us to make a country 100% renewable, so 100% integrated country. Okay, thank you very much. We'll be happy to answer questions. I don't know, I did not hear Thore telling me that I have to stop, so I hope it was not too long.
Thank you very much, François. It was not too long and very interesting. Thank you very much. I have got, it's now time for a few questions. And I have got one from Serge Bedard from Canada. And I just read it, Serge, and you can add if you want to add something more. But this is a question to you, François. First, thank you for the very interesting presentation. In a retrofit case of an existing plant, can the projects be implemented in phase that are adding up, or the overall benefits would be obtained only if all projects are planned and implemented all together? Heat recovery, solar, heat pump, etc. So please, François.
Yeah, that's a very interesting question. In fact, I should have added to the methods that we need to have methods to plan the investments. And so that the investments are taken with the holistic target that is defined and where we account for all the opportunities. So for example, the lifetime of the equipment, it allows to see when it is the best time to invest into one technology or another one. And so it is very important to have this in mind. And I would say that you do not have to invest everything at the same time, but you have to make an investment that is compatible with the future. And each time you make an investment, and you have to see the lifetime of the new investment, and you have to be sure that this investment is compatible with the future and helps generating the future solutions.
Thank you very much. Does that answer your question, Serge? Obviously. Another one also from Serge. Thank you very much. Very interesting talk. This is definitely the picture of integrated systems at steady state and upon considering many assumptions. How robust and subsequently trustful are such complex systems in any material flows fluctuations? Could you please comment on that? About the fluctuations in such systems. Interesting also. Please, François.
Yes. So if you look at the picture here, it is for sure not a steady state system. So the cities is by definition really stochastic. So the industry is also stochastic, and you can see that there are storage times. And of course we have to because we are going to be connected to the energy system, we have to recognize what are the functionalities of the energy system. And the functionality is not only to supply the energy, but it's also to supply the power and to guarantee the security of supply. It means that when we design the system, there will be elements that will in the system that will not be operated 8,760 hours a year. There will be elements that will be there for doing the management. And there will be also, as I have explained, the need to cope with the uncertainty or the stochasticity of the renewable energy sources. So it means that we will have to have a very holistic approach where we take into account the storage, where we take into account the energy management itself, and even the long-term and the short-term storage. So what I have shown with the optimal scheduling and operation of the system was to use at best the capacities that we have in order to supply the energy needs.
Thank you for that. I have one more question, and that is from Brian Elmegård from Denmark. Thank you for the interesting presentation. Can you elaborate on the difference and similarity between industrial symbiosis and industrial circular economy? A challenge, François, please.
I will play a little bit with semantic there. Okay, the symbiosis is as I see it, is more at the local level. So we identify geographically elements that have the capacity of developing synergies and work in symbiosis. The circular economy is more bigger picture because it goes with economy and rely on the exchanges that can be at large scale, right? Now, something which is interesting in the future is the fact that the symbiosis will define clusters that will be closer to the users, and especially when they will be based on biomass, on local resources, let's say. And when considering at the same time the this use of the local resources and the geographical character or the opportunities that we have in a given place, then we will see that we will develop something which is more integrated and more efficient. And I would give you one interesting result that we have in one of our studies. So we were studying, do we have to recycle plastics or burn plastics when I have a district heating associated with the waste incineration plant? And what we have seen is that a priori, the plastic is fighting against the natural gas price for the supply of heat, except if you heat the city with heat pumps. While in this case, there is no need to burn anymore the plastics because the value has disappeared, and it is much easier to give a value to the recycling. This gives me then a part of the answer, because the symbiosis allows the penetration of the circular economy and give value to the circular economy.
Thank you for that. I think we have no more questions, and there is no more time for questions either. Very interesting. Thank you very much, François. Have you stopped your sharing the screen? Do that otherwise. And I ask then Simon to share the screen. And his presentation is called Assessing the Benefits of Industrial Symbiosis Measures in a System Perspective, Case Studies from Sweden. And that is by Professor Simon Harvey at Chalmers University of Technology in Sweden. Please, Simon, start your presentation. We can see your presentation now.
Okay, so I don't need to ask the eternal question, can you see my screen? Okay, thanks a lot. And thanks both to Thore and to François for inviting me to deliver this talk. So it's a pleasure. I'm involved being a professor in industrial energy systems at Chalmers University of Technology in Gothenburg in Sweden. And I've been working for many years in the field of process integration. And I'm both active in the EFCE energy section, and I've also been working together with Thore in a number of the annexes, particularly the annex on excess heat. And this particular presentation will in fact be illustrating some of the things we've been doing in that annex. So the topic in focus, if you remember Thore's 4 topics for today, but I'm particularly interested in maybe illustrating a few of the things which François just presented to us, and focus a little on the case study related to strategic planning of industrial or integrated industrial systems, thinking about industrial symbiosis, and taking into account the future, the unknown future, and touching on this aspect of ex-ante assessment. A few words about Chalmers. So we are based in Gothenburg. There we go, Gothenburg. Gothenburg is the largest port, in fact, in Scandinavia. and the university, or there is a Gothenburg University, and then we have Chalmers, University of Technology, and we focus on research and education in technology and natural science. We also, of course, have shipping-related training and research, which is obvious given our location at the port of Gothenburg. And we're, I would say, typical size for technical university, about 10,000 students. So a little about district heating in Sweden. District heating in Sweden, you can see here to the left, this is deliveries of district heat, or this is the energy supply, but it's following the delivery. It's well established in Sweden, and it's been increasing continuously. You can see there over the past 40 years. You can also see that initially it was essentially oil-based, and you can see there the CO2 intensity of heat, and that's been going down from the level related to combustion of oil fuels, and it's been gradually decreasing. As you can see here, a very clear phase out of fossil fuels, a major increase of renewables, and something which we will focus on here, this pink part, is what they call energy recovery, and that is energy recovery from waste to energy. It's heat pumping, and we also have industrial excess heat, and that's what I would like to focus on a little. So a lot of well-established recovery of excess heat in Sweden already. But this is a case study about some of the problems or challenges in thinking about and investigating that type of project today. And Sweden is one of many countries to actually have a legal target for CO2 emissions. And you can see here that target is ambitious, net zero emissions by 2045. And that means that the energy sector, the industrial sector, the transportation sector, the building sector, the food and drink sector, agriculture, everyone is in principle aiming towards the same target. And that you could see here, if we go back to this one, in the days when energy or industrial heat recovery was feeding into a district heating system and essentially displacing oil, it was very easy to assess the possible benefits of industrial excess heat recovery. In a system where both the district heating system and the industrial sector are all on target to go towards zero emissions by 2045, that becomes a little more tricky. And I'll like to explore that a little in this presentation. So the real challenge for Gothenburg, and they are on target also for, I think there was something there which is important here. The district energy system in Gothenburg, they were aiming initially at the time we did the study to have zero fossil fuel usage by 2030. In fact, just after we'd finalized this study, they even decided to be even more ambitious and to move the time frame forward by 5 years. So they're now actually aiming for 2025. So very ambitious. The big challenge is they have a natural gas combined cycle, which is the mid-range heat providing technology. So it runs about 5,000 hours per year. And it's running on natural gas. And that, of course, means a lot of fossil fuel usage in that system. And they've been looking into a number of solutions. One is to replace the natural gas with either green gas or green methane, which François discussed recently, or green hydrogen. Also been looking into seasonal heat storage. And the other two, which we will focus on today, was either to build a new biomass-fired CHP plant, or to look for other large possible suppliers of industrial excess heat. And what we were looking into is how to compare those two in a future where a zero emission society. And one possible source is a big petrochemical complex located about 50 kilometers north of Gothenburg. I won't go into the details there. It's essentially a classical petrochemical. There's a big light hydrocarbon cracker at the core, which is converting light hydrocarbons to ethylene and the propylene, and distributing those to downstream plants with different owners. So note that different owners making both specialty chemicals and also bulk chemicals, particularly polyethylene plastics. You can see there some key numbers for that complex: about 1 million tons per year of CO2 and about 150 megawatts of excess heat. And that is a lot, of course. And what we've done in previous work, and I won't go into this either, but we've spent a lot of time. This is where all these process integration background is very helpful, is that we have put together a lot of inventory of all of the heat sources, heat sinks in that complex in all of the plants, and looked into many different options for on-site heat efficiency, looking into trade-offs between on-site heat efficiency, so any energy exchange between the participating plants, and exporting it to an off-site heat sink, and particularly district heating. So a lot of data, and with that data, we've been able to do this energy and cost targeting exercise you can see here, where we can, with a reasonable degree of confidentiality or confidence, sorry. You can tell I've been dealing with legal issues this morning, but we've been able to put together a reliable curve where we can see, okay, as a function of the amount of excess heat available, what does it actually cost to collect that heat and make it available at the site gate, ready to feed into district heating system. And this is the heat sink, which is the district heating network in Gothenburg, and this is where we are, right here in the mid-range. So this is from January the 1st to the end of the year. You can see here there is an existing waste to energy CHP plant, which is the absolute baseload provider. There are two refineries in the port area, and they are delivering about 1,200 gigawatt hours per year of excess heat. And that is, in fact, the largest delivery of industrial excess heat to a district heating system in Sweden today. And if we look at that duration curve, this is where we are, and this is where that natural gas combined cycle has been delivering in the mid-range. And this is where a new bio-CHP plant or this new source of excess heat from that petrochemical complex could come in. And the question is to compare those two options with respect to economic performance and carbon footprint. And this is what we call ex ante, because we're thinking about ahead of actually an investment decision to come up with some numbers about not only the performance of that system today, but the performance during its entire lifetime. This is a question we've already put. So the district heating operator is, of course, interested in knowing which is going to generate most revenue and has the greatest potential for emissions abatement in the future. And that, of course, is very much dependent on energy prices, the energy market, the policy instruments, and the carbon intensity of the energy carriers in that surrounding system. And so this typically led us to work with some energy market scenarios, which I will come back to in a few minutes. But this is a tool we've done, and I won't bore you with how we built the tool or the different models in there. But we've been working on this for many years, and I think many people working on this type of topic have the same issue as we do, that if we're talking about industry, focus on industry, doing evolving their processes, and particularly today, as there are very, very clear constraints on carbon emissions and profitability, or performing carbon reduction measures in a profitable way. They all are faced with this, okay, in the future, what are electricity prices, fuel prices, and greenhouse gas emissions associated with energy carriers going to look like? So we've put together a tool, and that tool has been based on some assumptions, some simple energy market models for the biomass market, for the electricity market, the fossil fuel markets, worked with input data, particularly from the World Energy Outlook from IEA, and come up with some values here which energy-intensive industry decision makers can use to compare candidate energy projects and identify robust options. And that's exactly what we were trying to do in this particular project with industrial excess heat. So as I said, we've looked into the future. It's ex ante, so 2 scenarios. We look forward 2030, 2040. We got some input data at the time of the study from the World Energy Outlook in 2017, and looked at 2 types of scenarios. They have their more predictive scenario, which they called new policy at the time. They now call it STEPS, and the sustainable development scenarios, which are more backcasting. That is what would need to happen given that they would like to be at a certain point by 2050, if I recall correctly. The Nordic energy market was assumed to be carbon-free, regardless of scenario. The Swedish electricity market is essentially carbon-free already, and many of the Nordic countries are moving in that direction fast. One of the things which we did run into, which is a challenge, is our view of biomass and whether or not biomass is to be considered as a limited resource in the future. In the sustainable development scenario, we assumed that that's an issue, and that as the carbon price rapidly increases, to move things towards sustainable development or low emissions in this case, we've assumed that biomass resources essentially run into their limit, and using more biomass at one spot is going to lead to increased use of fossil fuels elsewhere. Whereas in this new policy or STEP scenario, we assume that that's not the case, and that leads to more moderate price increases in the future. This is just showing some of the results. We've annualized the CapEx to do this. So this is the total CapEx. It's both the collection system at the petrochem complex plus the heat pipeline, a 50-kilometer pipeline, and connecting that pipeline into the district heating system in Gothenburg. So it's a combined CapEx. And we've annualized that, assuming a societal type of annualization. So we're assuming a 20-year lifetime and a 4% discount rate. And you would, of course, argue that that's probably not realistic for industry. We did look into that, but I will not deal with that in this talk. But we can see, of course, the excess heat, then we end up with a very heavy CapEx, some moderate O&M, and some very small variable costs, and that's primarily the electricity to pump and operate the system. And you can see here that this is the bio-CHP system with delivering the same amount of heat and the same amount of heat energy. And you can see there we have the new policy 2030, 2040, and the sustainable development. And we, of course, see that of course, the investment is lower for the CHP plant, but mainly the fuel costs are very different. And that's, of course, related to both the value of the electricity over time, but there was no great difference between those scenarios there. But it is primarily the very different acceleration of, or the increase of the cost of the biomass fuel, which is explaining those very big differences. And what we see there is, depending on what you believe about the possible availability of biomass in the future and how biomass can be expected, the cost can be expected to increase as policies become more and more constraining on energy system operators. Then we see that we reach some very different conclusions about the comparison between the excess heat and the CHP there. We also looked into the emission balances. This is a tricky graph to read. This is the avoided emissions related to implementing the CHP pipeline, or the excess heat pipeline, sorry, instead of the biomass CHP. The blue line is showing what happens in the new pulse scenario, and the orange one is the sustainable development scenario. And here we've assumed that the alternative use of biomass is in fact for substituting coal, and that leads to very high implicit indirect emissions by increased use of biomass in the CHP system. And that means we see very different results. So if we're assuming that biomass has a very, is in fact indirectly carbon intensive, then we of course see, as we would expect, that it's much more, it's a good idea to, or at least from an emissions perspective, to implement the district heating or the heat recovery from the petrochem complex. On the other hand, and this is the current situation, if we believe that biomass is not a limited resource, so there's only emissions associated with collecting it and distributing it to point of use, then we see that we get a very different picture, and we in fact see increased emissions. And what we see here on the x-axis, this is the carbon intensity of electricity. So this is today basically low emissions associated with biomass, and if we say that at least for exporting electricity to other countries in Northern Europe, we're maybe somewhere here between 200 and 400 kilograms per megawatt hour, then we're seeing definitely that it's better to run the bio-CHP plant. So this is knowledge base for industrial decision makers. So this first point was what we basically said. One tricky issue here is that I think everyone agrees, or there is quite a lot of agreement that biomass prices will increase in the future. But it's at least we have not yet run across some definite market price models which could really, with confidence, predict how that those levels could be expected to increase. So that's one degree of uncertainty. The other one I touched upon briefly was that we probably the 20%, the 20 years 4% discount rate is not realistic for industry, and that means that we, as in fact François indicated, that there's probably opportunities for third-party investors to begin to build that kind of infrastructure so that the different parties involved can handle different views for return on investment. The GHG we've discussed there. The excess heat could certainly facilitate the energy system operator to become fossil-free. But we said that the conclusions there are very dependent in the long term about what we believe about both the carbon intensity of the power section and, more importantly, how biomass becoming a resource, a limited resource, how that in fact impacts the global emissions. And that is a very tricky issue, of course. Another thing which I would just like to end up with is this issue of possible game changers. The petrochem, we assume that there are no major differences in that petrochem complex. One issue which has been discussed a lot in Sweden and elsewhere is, of course, carbon capture. And if we look at district heating today, well, they're both receiving deliveries of industrial excess heat, but also CHP plants are also delivering heat. And in Sweden, those CHP plants are almost exclusively run on biomass or waste with a high degree of biogenic content. In the future, and maybe not so distant future, we're working on lots of projects with the Northern Lights project. Then decarbonization is becoming an issue, and the heat, of course, instead of being delivered to district heating, could instead, the industrial plant manager may want to recover that heat to keep the OPEX down for carbon capture. And the CHP plants may well want to do the same thing, capturing their own biogenic carbon as a way to deliver climate services and to generate a different type of revenue. And that, of course, brings us into a situation with competition for heat. And that's, of course, where having heat integration under control is very important. And that's a project we've been working on in a refinery, where we're thinking about adding a CCS capacity to the hydrogen production unit, which requires about 50 megawatts of heat. This is one of the refineries in the Gothenburg port area. There are lots of possible sources of heat to drive that. There are process coolers could be rebuilt to deliver heat. There's a number of switchable drives, which are primarily run on steam drivers for the moment, could be run on electricity instead. There is some excess capacity in some of the heat recovery steam generators. And of course, we could put in new capacity. If we crunch all of that and optimize and see, okay, what's the likely way to deliver if we have a view of the operating pattern of the refinery over the year. We can see, first of all, there is vented steam, in fact, in that refinery that kicks in first, using some added capacity in the heat recovery steam generator comes in. And then we have what we call here HCN, heat collection network. And that is essentially, this graph is showing that most of the excess heat available at that refinery kicks in. And in fact, even just to satisfy the HPU, steam demand to run CCS in that plant, we have in fact having to operate boilers with purchased fuel. And that refinery, well, the HPU is about 40% of the total emissions. So the point I'm making there is this issue of trade-offs and a holistic system perspective for many new areas of competition for excess heat. And that's one of the issues we're in fact looking into in this IEA Annex 15, is these trade-offs and competition. So last slide here.
Okay, Simon.
Yes, just I think I can wrap up there.
Okay.
I think, yeah, I'll leave it over to you. I think I've said all of what we have there. So thanks a lot for listening.
No, take the conclusions very quickly.
I thought you were trying to tell me to stop.
No.
Okay.
Wrap up very quickly.
Important points
please,
here.
Please.
Of course, we need process integration methods more and more. Definitely, we definitely, as in François' beautiful diagrams, we really need to take the holistic approach and the symbiosis approach. And we really have a challenge in process integration and energy symbiosis that we have. It's moving targets everywhere. Everyone is more or less responding to these political signals for rapid and radical transformative change. And that means that assessing the benefits of isolated energy measures becomes more and more difficult. And of course, energy market scenarios is one of the many tools which we need to tackle that. So I think with that, I will conclude my presentation and see if there are any questions.
Thank you very much, Simon. Yes, there are a few questions for this very interesting presentation also. I have one from Ivan Cantor, and that is a question for Simon. With the amount of excess heat available in the industrial complex and likely at various temperatures, are there opportunities to reuse the heat locally before sending it at low temperature to heat houses? I know that you have worked with that, Simon, so please.
Yes, okay. Well, there, of course, there are many aspects to that question. One which I didn't go into here was the fact that I presented a slide which made it seem as if that we were primarily seeing CCS and district heating as head-on-head competitors for excess heat. Of course, one thing which is important is that the CCS plant, as any plant, is the energy cascades through there. So we supply heat at medium temperature, but there is heat which is leaving the system at lower temperature, which can be recovered to deliver district heat with or without heat pumping. So that's one issue. And if I understood the other part of the question, that was more about using the heat locally, and this was probably the petrochem. And the question, I assume, was delivering to district heat locally instead of 50 kilometers away. I'm not sure if I quite understood. That's how I understood the question. And the answer to that, of course,
I think, Simon, I think it may be about using it internally in industry before sending it out.
Yes, all right, yes.
I understand it that way.
Yes, well, I think I showed that diagram showing there was an availability of excess heat and what it costs, but that was the availability of heat after making the cost-effective energy efficiency measures on site. So heat recovery on site went first, and these 150 megawatts were in fact what was left at the outcome of that. So that was a net result at the end of the game, which I didn't go into those details, but we looked into that quite a bit. So this was not being voluntarily leaving inefficiencies in the industrial processes to enable exporting as much excess heat as possible.
I have one more question from Serge Bedard, which I think needs a rather long answer. So answer it very quickly, and then you can talk later on about this. Could you please explain what is considered as acceptable forest biomass for CSP applications in Sweden and in your model? Is it only forest residues and low-value trees, or any fresh cut trees from a sustainable forest is also available from a GHG perspective? A very short answer for the moment, please.
Yes, okay. The short answer to that is that the CHP plants in Sweden today are primarily fueled by forest residues and cutting residues, branches, tops, and so on. Almost exclusively. The rest is being fed as feedstock to the pulping industry and to the sawmill industry. Yeah. That is the short answer there.
Thank you very much. It's an area to be discussed further, definitely. Thank you very much, Simon. And then I give the floor to François, who will moderate the two last.
Okay, so I want to confirm you can see my screen and my voice is clear enough?
Yes, it's okay.
Okay, so good evening and good afternoon for everybody and the audience from the screen. And today is my pleasure to share some of my knowledge and the thinking on the issue named the intersymbiosis. Actually, I've been doing the research in this field for the past 7 to 8 years. Today, I will introduce maybe from the tools, that is how we can utilize some tools like the material energy flow analysis to make some support to the design and evaluation on the intersymbiosis. Okay, so I will speak about what is the intersymbiosis as a system innovation, and also the tools named the MEFFA, and to utilize the tool to analyze the so-called interim metabolism. And then I will introduce some case and the real case actually to showcase the application in the steel plant, the intercomplex, and also I want to share some of my thinking for the future vision of the topic. Okay, so I think we have to know enough for the information and knowledge on the intersymbiosis. Actually, it is the system innovation. That is a very brief the figure to show what is the symbiosis. That is, we want to transform our system from the linear one towards the more circuit system by, for example, by strengthening the collaboration and the change of the material energy flows between the companies. So by making this one, actually, we not only to change for example, the material energy flows in the network by establishing the synergies and the process integration in and between companies. Actually, we also change the perception of the companies and also to build the new market for our resource. For example, before the weight is only weight and with the zero value on the market, but now if we build the intersymbiosis, actually we put the weight onto the market and will become the resource for the other companies. So in this way, actually we build some new business model to forward circular economy. That is the benefit for the intersymbiosis. And of course, it will also to increase the benefit to our environment. So it is actually a solution to forward and to advances the so-called sustainability for our world. That is the value for the so-called intersymbiosis. So actually, the symbiosis is not a very new. Actually, we can see there's the many cases to show the natural symbiosis from the different animals and the organisms, and then borrow this idea. Actually, the human beings learn this idea from our nature mother and to build the symbiosis for our companies and for our real world. For example, one of the most famous one for the symbiosis is the one in Chalmers. We have the growing symbiosis in different companies in the Chalmers in Denmark in the past 30 to 40 years, and by by making the change between of the material energy resources between different companies, we can save the energy, we can reduce the emissions, and we can save the resource, and we can create the economic value in the market to forward the innovation for the environment. That is a very big value for promoting the symbiosis to the industries. And of course, if we look into the nature or the unit for the symbiosis, so actually it is some issue related to the process integration. That is today's topic for my presentation. So that is how we can look into the symbiosis from the process of the integration perspective, and how we can develop tools and the model to analyze is very critical to forward the innovation for the symbiosis. Okay, that is the very basic unit for the inter-symbiosis. We can see that is we have the different processes inside companies, and also we also have the different processes between the different companies, and we even have the different sectors in our bigger economy. So if we can make some proper analysis on the input-output flows for each process, and based on this one, if we can design the certain and the useful the process integration and the sectorial integration in a broader scope, then we can build a symbiosis for the network and also for the industry part. That is what we have done in the realities. So our work is how we can analyze, how we can look into the unit of the symbiosis, and how we can design a better and more efficient symbiosis. It's a very big topic for the issues. So to do this one, actually we want to make some fundamental model to analyze the issues. I didn't want to show the very details for the equation for the model. I want to just share the ideas how we can make the model and to analyze and to use the model to support our promotion on the integration of the processes, and how we can use the model to make decision support to the design on the symbiotic network. Of course, the very basic unit is the process model. We have the input flows and outflows, and also some recycle flows, and they should follow the basic rule of the balance. That is we have the very basic balance model, and for the one process. And if we can analyze this process very clearly, and then we will find the potential to make the process integration. Then we can build the process model and the process integration. And finally, we can get a broader scope. That is, we can integrate different processes inside one company or inside different companies or in the park. That is, we want to link the different processes and the different companies or even the different sectors in different scope. Then we can build the inter-symbiosis and also even the broader the regional symbiosis in this way. And of course, they will follow the rule. That is, for each one, they will follow the balance rules. That is, the input flow will equal to output flows, and for each sector they will also to follow the same way. In this way, actually, we can open the box for the symbiosis and to see what happened inside, and then we can design the better one for the future. That is how we can apply the model into the symbiosis network. Okay, so based on this material energy flow analysis approach, we can do the different work in the I will introduce in the later slides. The basic idea is that we have a different process model for each process inside the companies, and the different processes between the companies, and also the process integration and the sectorial integration between the different sectors, for example, different industries, the power plant and the iron steel companies and the cement and chemical companies, and even the waste incinerations. And by open the box, by look into what happened and the flows of the underlying materials in each process, we can design the very proper process integration. For example, this one, we can link the P1, P2, and until the Pn. And also by looking the flows into the different processes, we can further to analyze how we can project the different technologies into the process. That is the nature for the process integration, and how such projection of the technologies will also to change the flows and will to change the networks and will to change the different outputs or the impact to our environment. Then we can design the very proper the sector integration and the process integration to build them together to be the symbiotic network. That is from the process balance to the process integration until the sector integration to form the very rational and efficient intersymbiotic. That's our target to apply the model into the real case. And by making this model, we can further to analyze and to evaluate the different impacts from the design of the symbiotic. For example, the energy consumption and mitigation in the future scenarios, and also the carbon mitigation in the future and the scenarios. That is the basic idea to apply the MEFA approach to analyze the process to design the symbiosis. And by making this one, we can apply them into the real case, and I will show the progress on the different cases in different scope and in different target. The first one is I want to introduce maybe very basic information on the iron steel companies. We know the iron steel company, the process is very typical, the long process industry. For example, we have the traditional, the iron steel making process from the coking, sintering, and and maybe the different one. So different processes, and we make them together to produce the crude steel or crude steel and the final products, for example. That is the case. And then in these long processes, we have the different materials input and output. We have a different energy input and output for each process, and they will generate different impacts to our environment. And then the whole process actually is very material energy intensive. That means there's a huge amount of carbon emissions and resource consumption within the processes. So how we can analyze the processes, how we can design the different process integration, how we can design the symbiosis between the iron steel company and the nearby companies, and how we can project the certain technology to reduce the energy and resource consumption is a very big task for our scholars. We also to know that is because the whole process is very material energy intensive. That means there will be the source for the waste heat from the plant. For example, here is the typical waste heat happened in the iron steel plant and the processes. We have a different heat and the waste heat from the different processes with a different nature and features. For example, in different temperature and the pressures. That means that we can utilize the waste heat in different ways that is more efficient to making the benefit. So how we can apply the material energy flow analysis into the analysis on different process, how we can diagnose the waste heat source and the potential utilization format for the different waste heat will be helpful to design the future scenarios towards the low carbon transition for the companies and for the whole industries. That is I will introduce in the later. Okay, so based on this idea, actually, we can apply the MEFA approach into the different scale and the target. The first one is very basic to analyze the process balance for the iron steel plant making process. So here is actually so here we do maybe some lectures analysis. For example, we know for the whole processes, we have the materials and the energy input into the different processes. We know the carrier for the energy is the materials. For example, the energy from the energy and heat come from the coal and the coke into the steel making process. So by analyzing the material flows and also the related energy flows into the material flows, we can diagnose and we can analyze the very detailed and the material and energy information for each process in the steel making plant, so as we can uncover the potential to reduce energy to use the more heat source and to design the different symbiosis for different processes. That's the basic idea. So that is why we call it the material energy flow analysis. Okay, so here's the basic material flows for the steel making processes. We have the different process and the different type of the materials will run into the processes and to generate different impacts and waste to our environment. And at the same time, based on the material flows, they will carry the heat and the energy sources. So based on this material flow analysis, we can also to get the energy flow analysis for the whole steel plant. So here's the flow of the energy in the calorific value. We can see that is by analyzing the material flows, we can clearly to identify and to analyze the heat potential for each process. Then we can think how we can reduce the heat loss for each process and how we can design the process integration and how we can design the projection for the technologies to reduce the energy consumption to enhance the efficiency for each process. Then by making this one together, we can get a figure like this way. That is for the process integration. By analyzing the module energy flows for each process, we can make them together to be the whole system. That is the process integration. And by making this process integration, actually, we can identify the technologies, projection, and potential, and also we can also to analyze and to design how we can make the process integration with other processes. For example, maybe how we can link the iron steel component with the chemical component, and how we can link the iron steel component together with the cement component. And then we can find many solutions to reduce energy consumption and the waste generation in the different scenarios. That is the basic idea from the process balance to the process integration and to support the design on the symbiosis network. Based on this one, we can apply the model into the different cases and target. The first one is we can identify the heat potential come from the different processes. Here we have an idea of how many the flows, and then we know for each type of the materials energy they have the different feature. So by analyzing the different feature of the energy flows, we can further to quantify the source, the amount, and the feature for each the heat come from the process. For example, for the coking and for the sinter and for the BF processes, how many the waste in wood format and in how about the feature for the heat, we can have the clear information for each processes. Then we can make the heating map for the component and for the part level. Then we can have a think how we can utilize such heat into different ways and how we can recover the heat into different ways, and how we can design the symbiotic and the process integration to have a better utilization of the heat. That is what we can get the information to support such ideas to the design. That is, we want to analyze the heat and to analyze the future potential to recover and to reuse the heat in different processes based on their detailed information and the features, the temperature, the pressure and amount, and also the possible way for the utilization. Then based on this, we can further to analyze how we can project the different low carbon technologies or emerging technologies to reduce the consumption and to enhance the efficiency. That is, we can apply the model into the micro level. We know that is the basic material energy flows in the steel making plant into different process. That is the process integration. And by making this chart, we can find the very detailed information for each process, the flows quantity and the heat quantity and the energy quantity. We know the effect of the effect and impact for the projection on the technologies. The technology will affect the material flow and energy flow direction and amount. So if we can analyze the very detailed flows information for each process, we will know the very basic but the beta as Europe scenarios before and after the technology the projection. Then if we can analyze the flows before and after the techniques integration, we can quantify and we can assess the real impacts come from the different technologies. For example, here I want to show the three cases. This is the CDQ, that is the coke dry quenching technologies, and also CCPP, the combined cycle power plant, to use the heat to generate the power supply to nearby regions, and also some CCUS technologies, that is carbonate. We transform the carbon element from the slag into some other products to reduce the carbon emission from the plant. So by analyzing the flows before and after to make the techniques, we can analyze the benefit and the cost for the technologies. Then they can make the simulation on the detailed information. For example, if we project the technology into the different rate, for example, maybe 20 or 40 or 80%, and how about the benefit and the effect, and how about the cost, we can analyze such information by analyzing the flows, quantity, and the information. Then we can make some evaluation on how we can project the technology into different scales. Then we can have a clear information. Then we can design the future scenarios. For example, in each region, in different region, and in different companies, they can project different technologies in different scale, then we can get different results. Then we can make a combined decision-making support for the company and to the government peoples. And also based on this one, we know that is the interest symbiosis come from the process integration and some new technology, the utilization. So based on this, we can further to apply the model into the method level. That is how we can support the design on the interest symbiosis and to make the simulation on their impacts and the effects. So still here's the process for the iron steel plant, and by analyzing the processes and the different material energy flow in the process, we can find the different point for the integration. For example, how we can integrate the outside flow, for example, with water or with plastic into the furnace to become the new process integration. In this way, we can utilize the steel plant as a hub to form the central, maybe in the urban level to form the new symbiosis, to accept the different weight come from the city level, and also to supply the different source from the steel plant to nearby region. For example, to supply the heat to nearby hotel and commercial areas. In this way, we can realize a low carbon interest symbiosis by making the steel plant as a hub in the whole, the symbiotic network. Of course, the fundamental information and the basis is we analyze the different processes and we design the different process integration to form such a symbiosis to forward the future development and towards the low carbon future. So based on this idea, actually, we can promote the plant in this way. That is a typical the with heat source from the steel plant. That is the heat come from the different processes and with the different the temperature and the pressure. Of course, based on this one, we can design the usage for the heat into the different component and areas. For example, we know that is the low temperature heat can be utilized by the nearby hotel and the commercial areas to supply the hot water to reduce the coal and natural gas consumption to realize somehow the carbon mitigation for the nearby areas. And also for some other heat, for example, the heat comes from the blast furnace and the coke oven gas and the LDG, actually, they not only have the calorific value, they also have the carbon and the hydrogen elements. That means they have the potential to be the raw materials for the chemical company. For example, to utilize the LDG and the COG to produce the methane and some chemical products. In this way, actually, we not only to translate the symbiosis, but also we to change not only the supply chains, but also we change the value chains in the circular economy strategy. Why? Because we know that is to become the primary product, for example, to become the hydrogen products, actually we increase the market value to the with heat. Remember, the heat is a very low value. So if we can utilize the heat not in the calorific value way, but also to utilize the material source from the with heat from the plant, actually we can generate the higher value added the product in the market. So it is a way to enhance the value chains by analyzing the potential for the usage way for the heat. That is the enlightening part for the company person. So by making this way, we can find this actually by analyzing the process analysis, actually we can design the symbiosis based on the life cycle, the way that is we expand the longer life cycles for the companies, not only to recover, but also try to use the heat into the higher value in the market. And also not only to rebuild the supply chains, but also to analyze the value chains together with the material flows in the supply chains, and to create a higher value chains in the future. In this way, we can realize a more efficient and more the beneficial way to design the symbiosis. This is the benefit come from approach to the design towards a better way for the symbiosis.
So it's time to conclude, huh?
Okay, so then I will show the real case. Actually, that is the model application. For the real case, actually, I want to show you a real case in Japan. That is we know. So if you travel to the Tokyo, that is Tokyo and Tokyo Bay, you can see here, actually, the areas nearby the Tokyo Bay, if you travel from the Tokyo from the north to the south, you will go from Tokyo to nearby Kawasaki and also the Yokohama cities. So these areas, the industrial areas for Japan, we know nearby the sea means easy for transportation. So actually they want to apply this idea into the Kawasaki. You can see in Kawasaki they have many the plant, the iron steel company, and also some many the chemical companies actually inside the cities. So idea is we try to analyze the flows in the city and into the different the factories, and we try to forward the flows from the single and linear way into the circular way. That it means we want to build a urban industry symbiosis network for the whole city. In this way, we can realize a very low carbon or even a zero carbon emission city into the future. That is the idea of applying the symbiosis idea into the whole urban planning and the industry planning in the case. And so of course, to realize this idea, we also need many the concrete technique. For example, we need many hardware technology to support the transition for such idea. For example, we need the technique, for example, to RPF to utilize the waste to the furnace in the companies to make the incineration and to make generation on the steam. Then we can realize the process integration by using the different advanced, the real technologies. That is the how we can realize in the realities. And then of course, we also need to analyze the different processes in the single component, and also the different process integration potential between the different companies. And we design the symbiotic network into the local level. That is the different companies and their heat potential and for the supply and for the acceptance. And then based on this such information, we can design the possible pathway to utilize the local heat into the different way and into different scales. Of course, the scenario have to be done step by step. So we design the scenarios into different steps. The first one is that is the different scenarios. We design the heat network into the different steps. That is to utilize the heat. Maybe there's no utilization, and we use the heat in the very short distance. For example, the very close companies will change the heat to each other. For example, the R is only 500 meters. And also in the near future, we can extend the network into large areas. For example, we can realize a heat network with R equals to the 1 kilometers. And finally, we can even to realize a heat network with R equal to 2 or even 3 kilometers. In this way, we can transform the process integration to the different component integration, that is the industry symbiosis, and even to a regional or the urban symbiosis. That is the basic idea to exchange the heat network and to utilize more and more heat in the future to reduce the carbon emissions in the whole cities. Okay, so finally, I want to share some future vision and my thinking on the topic. For example, we know that is we have here. I want to share the two thinking. The first one is the toolbox supporting the design and analysis on the process integration and the industry symbiosis. We know the symbiosis in essence is the process integration into the different level, from the process integration in the company, between the company and in the regional level. So there are so many tools can support this idea. For example, today I share the very fundamental tool named the material flow analysis and also life cycle assessment. And also I also have the very basic tools like the systematic dynamic approach and also the pinch analysis. And also in the future, we know that is the realization of the symbiosis, not only the process analysis, we also have to think about the spatial issue and also some commercial model. So we can try to include many different tools, for example, the economic method and also planning approach and also the product approach together to support a better and more feasible planning on the symbiosis in the different scope. Then we can realize a reasonable, feasible and efficient the network in the future. So we try to combine the different toolbox to support these issues in the future. That is the first one. The second one is also to know that is now that we have the different smart technologies. For example, we have the cloud server and the big data and the monitor into the processes. So how we can utilize the digitalization technology to support our design and analysis is also a very big challenge for the scientific and the scholars. For example, we know that is one big challenge is how we can design the feasible and also the reasonable future scenarios. So we can utilize the different the ICT technique to support the design on the scenarios. Okay, so how we can do this one? That is, for example, here's one case we do in the senior Dutch project. That is, we have the
Liang, we have to stop, otherwise there will be no more time for the rest of the speakers.
Okay, okay. Okay, that is the final slide. Actually, that is a case for to show the smart technology, and also we can analyze, we can utilize the smart technology in this way. That is, they will provide the real-time information, for example, by minute and by second flows data in the process, and this one can help us to improve our model. And if we can utilize the real information from the monitoring technology to support the improvement on the model, then we can design the better symbiotic network in the real case. And then as a return, actually, they can also to help us to make the verification. For example, after we design, we can utilize the ICT to monitor the progress. Then we will know whether or not we will realize the scenarios in the future. So they will also to provide some verification for our design and analysis in the future. So anyhow, we can use the ICT to monitor to verification to verify our benefit and the result in the future to make a really the very feasible and reasonable the low carbon scenarios in the future. Okay, fundamentally, I want to share with some future challenges for discussion. For example, we know we have the very emerging ICT technologies, and they can offer the better data and dynamic and real time, but many models didn't have the interface to accept the data, so that's a very big challenge. And also, even though we have the data and the result, there's still a lack of the bridging the policy making and the evidence come from the model. So that's also the challenge. And then we also to know that is how we can design the very scenarios, very good scenarios and scientific scenarios. It's also the very big challenge in the future. Okay, so that is my presentation, and thanks so much for your attention, and welcome any comment or questions for this topic. Thank you so much again. Okay.
Yeah, thank you, Liang. So I think that we do not have time to have a discussion, but I will take this the opportunity of the full discussion to also perhaps take some of the answers that you have, or the challenges that you have been discussing, to open the floor to a more general discussion. So could you stop sharing your screen so that I can just highlight my so the goal of this part is to introduce a discussion with the panelists with the 4 topics that Thore has been introducing. So we are going to start with the methods, and then Thore is going to continue with the ex ante demonstrations. So I guess that you see my screen. I have not, so it's very special because I would like just to introduce the subject, and then feel free to raise your hand or to ask questions in the Q&A. So the idea of this topic is the discussion is, do we need new methods? Do we need new methods to integrate the new technologies? What I have learned from your presentations is that there is a need for something which allows us to do the design, that the design needs to integrate operation, and the design needs also to integrate the planning of investment. So it's not only a single shot or unique solution, but a full design. And I would add to this the need to handle the uncertainties. One of the challenge from the technology point of view is that the next systems will see a high share of renewables in the industry or in the energy system, which also means that we will have to look at the integrated waste management, waste or mass management, the CO2 capture that has been always highlighted, and the need for looking at the power to gas that introduces, in fact, the dimension of the energy management. So which is by definition multi-energy, and that has to integrate the supply chains. And at the level of the decision support, the methods needs to have the appropriate metrics. There needs to be multi-criteria, and you have really shown this, Liang. There is in all the presentations a list of solutions that are presented, And to some extent, there is also something that is important, is to be able to highlight the value of the constraints that are imposed in the system. So this is a brief summary, and from there I would look in the Q&A. I will leave my screen there, and I will take the questions if there are. And if someone wants to raise the hand, it's also possible, and get access to the discussion. Just to inform you is that Simon Harvey had to leave because he had to teach, and so he passed the regards to all the attendees. So the floor is open to questions. So who has a question or a reaction from the panelists, of course? So there is no questions coming from the Q&A for the moment. I don't see if someone is raising the hand. So if you go into yeah, yes, please. Sorry. Okay.
Berntsson was supposed to be here. She is from Chalmers, together with an aspect about new methods, and that is new methods taking into account combination of power, electricity, and heat, and also the variations in the electricity use in industry, and the situation in the grid in the future. So an area for new methods, as she has pointed out, which I agree with.
Yeah, I agree. So the system, so a multi-energy systems is for sure important, and something which is also very important is to have this mass and energy integration done together. Okay, I don't see if so please don't hesitate to ask questions. So because I see that some people are leaving, so we please ask questions, and if there are no questions, I would just perhaps ask Luciana, or okay, there is one. It's Ivan Cantor. So he's saying that many of the presenters are developing methods, tools, or example of process integration. What are the barriers for deploying these methods broadly in the industry?
I would say that the application of those tools, it's mostly challenged by the industrial context, by the operator on site. It's not always easy to come up with a solution that they are easily implemented, unless they are in line with the acceptance of industry and how they operate the site. We are now, I see, trying to expand, going beyond the boundaries of a site to integrate multiple plants, but what we see in industry is that there is a lack of communication between different departments. So the control that happened in one department and versus the other, the priorities of one department versus the other could limit the integration that can occur between departments. It can be also a safety requirements that limit the implementation of some projects, and the comfort that operators could accept for some implementation. Just to name reuse of a contaminant condensate that could be occasionally have some issues smelling or something like that, could immediately put a stop on projects that could save water and save energy in craft. But of course, mitigating the risk, taking all the precautions to have a good ventilation system. So it comes to expand beyond the boundary of that particular project and to accommodate other requirements that industry has to implement projects. And it starts a lot with also operation and control and interaction between different departments.
Okay, so Thore, Liang.
Okay, so I want to say something about this. Actually, it's a very good question, and we know that the industry person is very different from scholars. That is, they are very cost sensitive. They want to know the very detailed and economic impacts for our design, for our analysis. But actually, many research and also many, for example, the paper and the calculation didn't include such part. We know that is to make the new process integration and to utilize the new resources. We need a new investment for the facility, for example, to the new facility to use the biomass or some renewable energies. And also we also to know the benefit. We make a simulation on the different benefit, but such benefit usually is in the long term. For example, in the long future scenarios. For example, in the future, if the carbon price will increase to which value, then they can get the benefit. So they didn't see the very clear the information on the cost benefit. That is will make them very reluctant to make some innovation or to make some change on the current systems. So actually, when we do some project in the local scale, actually we make some, for example, we make some the design of the business model as well together with our design on the product integration. Then this will be more welcome by the company person. They want to know, for example, the payback time will be how long, 3 or 2 years, and 1 year is better. And also they want to know, for example, they want to know how they can get some financial incentive from our design. That also their interest. So if we can design the product integration together with the business model and the financial, the package, they will be very welcome to our design. That is a very, maybe the lacking point for the current research and the implementation for the project. And the second part actually is also some, I think some log effect. For example, some person in the company, they are very reluctant to make the change because if they make the new process integration or the new processes, the old person will lose their job in the future. That is their concern actually in the real case. So how we can make the better design and also the better innovation, not only the process, but also on the economic and on the commercial issue is also a very important one. This is actually some information I get from the real project in the local level. This is, I want to share such information to the audience and to the scholars. Okay, thank you so much.
I would just like to add that in my experience, industry has now many more parameters to take into account in their decisions. It changes in policy instruments, for example, and restrictions on CO2 emissions and economic changes and such things more than earlier, which makes more interested in working together with people having developed more complex methods. That's my general experience recently.
Yeah. And thank you. And from my side, so I would just give also a small answer. So one of the barriers is to have people trained. So it means that teaching is very important. So and even introducing this in continuing education is most probably something that is a key. And the other key is to listen to the questions from the industry, because at the end, what we have to provide them is not the good solution, is the correct solutions that they are convinced with. So it means that we have to be able to listen to give them the arguments to take the decisions. Okay, I'm going to take to give.
Can we go to the second one?
Yes. So I have another question. So it's Etienne Bernier. So from our point of view, an important methodological challenge is the proper choice of the counterfactuals. So for electricity to fuel, would the electricity be otherwise curtailed, or would it substitute fossil fuels for industrial heat? Would the CO2 be otherwise emitted or otherwise sequestrated? And the same, and for the biomass to fuel, would the biomass otherwise be left to rot, or would it be left standing, or perhaps otherwise sequestrated as well? So from I'll let you perhaps react, but it's clear that the substitution mechanism is very important, and this introduces, at least from my opinion, the need to have a vision about the system. So it means that we cannot always substitute what was easy to substitute, but we have to look with the competing technologies, and with the competing technologies at the level of the energy system, and not only at the level of the company alone. And so I fully agree with the difficulty of defining the right substituting mechanism, or the right method to measure the impact of what we are doing.
So I want to add more.
Can I take the screen? Sorry. Oh, sorry.
Yes, if you want, yes. You have it, huh?
Yes.
So while you're showing this, because there was a question that was more or less related for the estimations from Serge Bédard. So for the estimation of the environmental value of synthetic natural gas, what are the counterfactual that you are using to assess the benefits? The energy efficiency of the production is not that high, so it is valuable only when CCS is used. Yes, so I do agree. So that's and it goes in the same direction. Is the fact that when you substitute and when you look at the SNG, in fact, one of the value is the fact that the synthetic natural gas is a stored energy that is easy to distribute and easy to use in different types of applications, being for the transportation, for the heating purposes, or for the industry. And therefore, it is very important to have a vision of the energy system that even accounts for the variations, so the seasonal variations, for example, so that we can really see the benefit. And to be clear on the question of SNG, in the energy system models that we have for Switzerland, what we see is that we store or sequestrate the carbon dioxide in the winter period, and when we produce the SNG, and we use the carbon dioxide for storing an excess of electricity during the summer period. And it means that we have, at the end, a seasonal strategy for managing the carbon dioxide that is emitted during the production of SNG. And this is creating the value of the SNG. So it means that SNG from wood alone is not interesting, but SNG from wood with heat valorization and CO2 management, including the excess of electricity storage, is making a much higher value for the SNG.
Okay, can you see my screen?
Yeah.
Yes. This was discussed in, I mentioned this Vienna International Expert Workshop, and strategic plan of complex systems, and including process integration aspects then. And then it was ante means evaluation of technologies and systems at few functions in which process integration plays a very big role. and also the system changes and consequences of future economic and policy instrument conditions, which means that the decisions should not be taken with today's conditions about the economy and policy instrument, because they will change before new is installed, and definitely during its lifetime. So therefore, it's important to have future energy market and other scenarios also to be included. Simon showed one example of that. And furthermore, we have novel technologies coming. We have mentioned them: CCUS, electric refineries, digitalization, as examples of new processes which will be installed, but maybe not now, but in 5 to 10 years. So it's important to adapt also in process integration aspects to identify opportunities for such new technologies later on. So this is very complex. Therefore, it's needed strategic planning, and also trying to avoid lock-in effects by doing the wrong thing now compared with what it should be in a strategic perspective. And therefore to have future conditions, but also to have designs which would work good today. So it's very complex, and so this was discussed, how to have methods and deal with this very important aspect of strategic planning in these systems. So I would like to have any about that, please.
There was a question by, I have a question by Enrique Matos, who is quite interesting as well. So several proposals for more sustainable scenario are based on the possible site integration. How could be possible to implement in real when the physical interactions between the companies is very weak? So I don't know who wants to start. I have an answer to this, because what we can see, at least we see it in Switzerland, is that there is a third party element that is the operator of the symbiosis. And that's something which we can see in the development of symbiosis, is that typically companies on a given production site do not have the exchange as their main business, but they can ask another company to make the business from the exchange. And so this company is going to take the risk, make the investment, and operate the exchanges. And that's and so if I'm looking at the clusters in Switzerland, for example, you have a company that is taking care of the waste and that is at the same time selling the steam to the industrial sites. And so it means that if there is such a unit or a company that is becoming a partner of a list of different partners, then the system can work, and the risk can be mitigated. And so what we have shown at least is that the third party company can make a risk, will make a financial analysis and risk analysis that will be different from the one from the different production companies on the same site, and the production companies on the site will still have a benefit. And so it will be then creating a win-win company with a window of profitability that can be shown. I don't know if
I would like to add that in our IETS work in about excess heat, which is a big cooperation in many countries, we also include the risk about cooperating between different companies and how to deal with different types of risks. Also have now a number of examples how that has been done in different projects, and how that can be overcome, those problems, which François also mentioned. Interested in that, there is information in our IETS work about such aspects.
I would add to that in some of the case study that we did, we encounter third-party units operating the utility system. And although it has advantages, it also has disadvantages, because it can put a new level of constraints on the process that it's supplying steam, for example, before it distributed. So it's important to create also those units in a way that the flow of energy, the flow of waste streams, for example, between those units is taken into account for the global efficiency. And I would add that probably some policy instruments will help to develop a better connection between different industry to facilitate such analysis and implementation. And given the aspect of circular integration, circular economy, new business models need to be developed to facilitate the exchange between companies and the implementation of such new avenues of enhance efficiency.
Yeah, thank you. So Liang,
okay, I just want to say very simple words. The first one, I think the spatial factor is maybe a precondition to realize the symbiosis between the different components. For example, if the distance is too long, the heat transfer will be not so feasible. So we should consider the spatial issue when we design the symbiosis. On the other hand, we can also to think that is the future scenarios is not only include the older one, but also we have many places to replanning or to planning in the future. So when we make the planning for such areas and companies, we can also to think about how we can utilize the current, for example, the company as a hub to try to make the best use of the resource energy for the symbiosis to these companies. Then we can attract maybe more related companies and industries to these areas to form the more efficient the symbiotic network. For example, in Japan, in Fukushima, in Japan, we know the nuclear plant is destroyed. So they build a new plant that is use natural gas. And natural gas will have the plenty source for the waste heat. So the local government planned manage the new greenhouse to utilize the waste heat from the power plant. Then the greenhouse can sell the very high value market, the agricultural product, for example, tomato and metal and watermelon. So in this way, we can realize the symbiotic idea in the new planning project. Then we can make the better use on this product integration and the symbiotic idea in the near future. That is I want to share to the audience and to the questions.
Thank you. I have another questions from Mark Perez Fortes, which is to all the panelists. So will COVID-19 have an impact on how the industries perceive their supply chains? Will this serve to the companies to likely improve their efficiencies rather than rely on globalization?
So actually, one benefit for the symbiotic, it can reduce the supply chain risk. So I think maybe in the COVID-19, actually, maybe the symbiotic can be the new driver to make people to realize, okay, we should build more symbiotic to avoid such risk on the supply chain. So maybe that is maybe some benefit we can get from the symbiotics to overcome the impact for the COVID-19. If we can make the proper design and the proposal to the company persons. So that is the very positive part I want to share. Yeah.
Yeah, if I may, I would go in the same direction. So the symbiosis is offering an opportunity. Now I'm not sure that it has been understood already. So it means that they still build solutions which rely on globalizations, having the impression that it will be cheaper to produce in China and import to Europe, for example, while in reality there is already some there should be some trends in making more local supply chains for what is critical for the society, and therefore not always relying on very long and globalized supply chain. Thore, I don't know if you have an opinion, or Luciana?
Yes, I can. I think although it opened new avenues, and there is a maybe a local context that can be beneficial, we are at large looking to integrate different industry sides, and even though it's possible, you need to have the infrastructure ready in place. And even though there are different alternatives that could be facilitated through the globalization, through the industrial symbiosis, taking advantage of those and switching from one model to another, because a situation like COVID creates an imbalance. It's not easy to switch from one alternative to the other unless there are proper infrastructure in place and proper models and connection in place. So I think it's important to have a backup plan and also put in balance how much such alternative could affect the main plan, and how they can be better utilized for in the end to deliver decarbonization potential and facilitate the switching between different options.
Yeah, I think that Thore, it goes nevertheless in the direction of the investment planning, and perhaps also to introduce a resilience criteria in the system design. So it means that not only we have to look at the efficiency, but we have also to be sure that the system will operate for at least reimbursing the investments, and this introduces at the end perhaps also another reason for promoting the industrial symbiosis. So otherwise, I have another question. In your experience, what do you think about the impact of the government to promote the use of clean energy via reduced tax, subsidies, or investment? Is it important, or does it really have a significant impact, and it all depends on private initiative? So it's a question from Jose Manuel Flores Perez. So I would say that so who has the best experience in looking at the impact of the government to promote the use of clean energy?
In Canada, we have a GLEAM program, and it's been promoting clean technologies in industry. So it's important, especially to make big changes, to have the incentives to ensure that the industry is moving forward with projects that are larger than 1 year payback. The important component is that moving forward with such investment, it's important to ensure that they are sustainable in long term. So this is what we are trying now to do. But I think having incentives, good initiatives on tax and subsidies, it's gonna be helpful for industry to take the big step, to make the game change, and not only going for the private investment.
So I think in the very short term, actually, the support from the government is very necessary to internalize the allocate from the such issues. So it's necessary. But in the long term, I think we should build a real business model to make the company to accept the renewable resources. For example, a very simple fact is if our raw resources is very expensive, the company will try to utilize more and more waste as a resource. That is a very simple reason, because the company person is very smart to find the cost benefit in the market. So in the long term, I think we should try to realize this one via the business model. That we should make the issue on the market. That is the long-term answer, I think. But in the short term, the government is still maybe very good support to the issue. That is my idea on the question. Thank you so much.
Yeah, Thore, you are muted. Thore, you are muted.
Sorry. Yes, I'm not. Yes, I think that governmental in different are steering very much the development in industry, and has let them have more strategic ways of looking at investments and changes than earlier on. So I think it moves a situation towards more strategic thinking, which is, I think, is very good, and that is definitely based on different governmental and regional incentives.
Yeah, from the side of Switzerland, there was also this trying to have sectorial agreements on overall energy savings that would then be allowing of not being punished. So the taxes will not be activated. So it's an indirect promotion there, because it's not financing, but saying that if you do nothing, then you will be punished. And this is something that is perhaps also allowing the system to self-react to a threat to some extent, and this creates then the possibility of seeing multiple benefits. So it means that in this case, the industry sees that there is, or learns that there is an interest in going into more efficient, higher efficiency, for example, which allows to activate the investment perhaps for other reasons. So sometimes it's just because you improve your image, but that at the same time you find solutions that are the best for you, because you choose the solutions. So they are not forced, and they are not artificially pushed into the market.
May I, or are there any more questions on this now? Or may I
but there's one more question to Lucine, and I think there's one more question on the chat box.
Luciana has mentioned the importance of new business models to drive the disruptive technology changes being evaluated. For the context of industrial symbiosis, or more broadly, the value chain level, are the basic tenets for the new business models obvious? What types of changes in business models would result in robust, deep decarbonization strategies?
I think at the base, business thinking, money talks. So it's important to have a more elaborate analysis of benefits of energy efficiency. And on the other side, in the context of industrial symbiosis, there is a new trend that waste becomes value. So putting that in perspective, I think it will create a new dynamic in the business, and will get more interest from industry to move into that direction. So seeing the value of energy efficiency, seeing the value of added value products, and how that will be accommodated in the new model. It's important, I think.
Yeah, I would say that from my side, but it's really my opinion there, is that the business models of today are in fact highly biased, because we never see we never see the investment for the fossil resources. We see the price we pay on the market, and in between there is the stock exchange that has played a big role, and the government that have used a lot of subsidies for guaranteeing the fossil fuel supply, which is going to bias 100% the energy price. When we are talking about business models, it's always interesting to see that when you do an evaluation of a project, at least from my side, I receive more questions of the validity of the investment that I'm doing than on the validity of the assumptions that the price of energy that I have used for my evaluation will be valid for 25 years. And in fact, the two are have to be considered. And this is, in fact, then going to ask most probably for new models in generating business, in which there will be new actors. So the third-party actors, for example, the one who take care about who take care about the exchanges, and even the one who supply the data for being able to make value out of variations, for example, will become new actors in the system. And if you think then afterwards on what is going to happen when you will manage the exchange by blockchains, okay, paying the real value for all what you consume and for the infrastructure that you access, then I'm sure that there will be new business models that will emerge.
And probably the new business model will be that company will purchase and merge between different type of industry. So it's not going to be a dedicated industry type, but kind of a partnership between industry and maybe mergers and acquisition in that regard.
When talking about business models and developments, and also taking into account what I mentioned earlier about the need for strategic, a serious statement from one of a CEO from a very big industry company, and he said a little jokingly but seriously also, every time when we have identified the very best solution to start and go on, the policy instruments have changed, so we have to rethink everything, which means that this strategic planning, introducing also uncertainties about future policy instruments and so on, and identifying robust solutions seem to be very important. And I think there is that could be one area to work also in international cooperation in that type of developments, both methods and applications.
I think when we design the business model, actually our researcher can try to search and for the company to find some policy credit for example for the related the project, and then we can incorporate such information into the design on the business model and to share such information, because sometimes the company person didn't know such policy or the credit from the policy, so we can share them such information and to input such information into our design business model. Then it will be more maybe the efficient to let them to see the benefit if they realize our planning in the future. That is maybe one credit we can share with the stakeholders for the company persons. That is also we have done actually in our local project. A very good way, I think. Yeah.
Okay, thank you. So Thore, I think that it's time to stop, because we are being late, and then I see that the people are leaving progressively. So I would like to conclude. So I will pass you the word. So Thore, because you have been managing this with me. So Thore, could you just say a word to conclude our webinar? You are muted, Thore.
Oh,
Okay.
now I have learned that. Good. Oh, thank you much for this, and we have heard very interesting in different ways, and one conclusion that can be made is that this area is extremely complex, but and also important. We have discussed many things. It's not any longer only about efficiency, about technology, about heat exchanges, about technologies and so on to put in. It's much more complex, and it deals also with policy instruments, the need for GHG mitigation in industry, the need for novel technologies and systems, which we haven't included yet in industry in practice, but we know that they are there and that they will come in later on. And that means that we must have methods. We must show industry that methods can be used in order to also to identify solutions which are good in a more strategic way of looking at it. In the Vienna webinar, workshop, that was discussed at length also to identify solutions which are more robust for the future and includes both technology, economy, policy, and so on. And I think that the examples we have seen today have shown that importance. I therefore think that very possible to identify a few areas to work further with internationally between groups that we have identified in this discussion and other groups internationally. So in our work in IETS, we would like to take contact with interested groups to identify what, how we could work together in networking, going more into detail, how we can share knowledge and share methods and experiences also from case studies. Thank you very much.
Yeah. And I would add from my side, because it's the also from the energy section. So I would like to thank everyone who has participated and attended to this webinar. So Giorgio, I guess that you are going to perhaps just indicate what where the people will get access to the recorded video that needs to be mostly processed before being shared. And from my side, at least, I would like to highlight the fact that, yeah, the international collaboration is in the form of creating projects together, having network of exchange, and the energy section is there. So there is an advantage of an energy section. The energy section is that there is no restriction of access. So everyone who wants to contribute can just send us an email saying that I would like to be part of this energy section. And something that we have in mind in the near future is to create a publication where we would collect opinions. So it means that everyone who wants to express an opinion on the use of process integration for the energy transition will be invited to contribute, and with the aim of having some sort of a short book, ebook that would be available for the whole world, showing and expressing the vision about process integration for the energy transition. So Giorgio, I guess that you will make a conclusion from the EFCE point of view.
Sure, sure. I think that Martin will be in a position to provide the explanation about, you know, access to data, registration, recording, etc. But I would like to take the opportunity to thank you, the moderators, François and Thore, and the speakers, in particular Luciana and Liang, surviving until this time, for very good presentation, very interesting. I've seen that the number of participant is still high at this time, so clearly there was a lot of attention. I see a lot of questions as well, which you have answered properly. So I would like to congratulate you all for a very nice work done today. And thank you on behalf of EFC. Martina, can you please give some explanation about what to do for the recording?
So thank you, Giorgio. For the recording, all the information will be on the EFC website, and you have got the link to go to the YouTube channel, okay? But it will take maybe 1 week for this, okay? So thank you.
Okay. Thank you very much. And don't hesitate to contact us if you want to be involved either in the energy section or on the IEA. So it will be a pleasure for us to collaborate with you, and see you next time. Okay, bye-bye.
Thank you.
Thank you very much,
Bye-bye.
everybody. Thank you.
Thank you.